welcome everybody to this EIS webinar. It's great to have so many of you joining. It's something that we've been looking forward to presenting to everyone over the last few months that we've been planning this. Just to give everyone a quick background, this is obviously a webinar that's being hosted by the Engineering Integrity Society. We are a long-established charitable organisation that is focused within the realms of fatigue, testing, durability, sound and vibration, and are comprised of members from within the engineering communities within those fields, many of us working for some of the best known companies in the industry with years and years and tens of years of experience, hundreds of years if you summed us all together. The EIS organises webinars and seminars like this to help to inform and to improve the knowledge base throughout the industry. We also hold annual instrumentation test and measurement exhibition, which has been in Silverstone over the last few years, which is always an enjoyable day. And we also generate a technical journal, which again covers interesting developments within our field of interests. The webinar today is being brought from the Young Engineers Forum. It's one of our main charitable activities to focus on developing young engineers within these fields. So on today's webinars. So we have two presenters today, so you're spoiled because we have two excellent presenters. I'll introduce each of them just prior to each of their presentations. One thing that I would just say is that they and the IS, and I'm sure everyone else listening in, will value any questions that you have based on the material that is being presented. So please, if you do have questions during these webinar presentations, if you could, as soon as it comes into your mind, pop it down into the chat function within Teams, then Sarah can compile the questions as we go, and at the end we will ask the presenter as many as we can within the allotted time. If we don't have time, by having the questions written down, we can make sure that any questions that don't get answered, we can still do that in retrospect, and that can be part of the offering later. All of the webinar will hopefully be available as a video cast at a later date, which will go up on our website and on our YouTube. So, with no further ado, we will move on to our first presentation. Our first presenter is Dyrr Ardash, who is coming to us from Williams Advanced Engineering. Dyrr has worked within the industry for over 20 years, primarily in powertrain development, working for companies such as Ford and Denso, and senior positions in both engineering and commercial roles at Ricardo, currently at Williams. And he is currently the business development team, working within the business development team at Williams. And he's going to speak to us today on the whole life cycle of the vehicle. So, as I say, with no further ado, please take us away, Dyrr.
Thank you, John, for the introduction. I hope everyone is well within these strange times that we are currently living in. As introduced, I am sort of going to give you a bit of an overview of the vehicle ecosystem sort of considerations. The intention from my side is a bit of an introduction into WAE, but also moving through the whole life cycle and the vehicle life cycle from a sustainability perspective, and give you an indication of what some of the OEMs are doing, and also what Williams Advanced Engineering are doing. So, first of all, a bit of introduction into Williams Advanced Engineering. We're formed in 2010 from the development of the in-house Williams Formula One KERS system. whilst our major markets are still automotive and motorsport, we are applying more of our core competencies into adjacent and emerging markets. We have three key technology areas of electrification, aerothermal and lightweighting, utilising systems engineering principles with significant capability and facilities to deliver boundary breaking projects for our customers. These are usually in very tight timeframes. A sample of our automotive customers is shown, but however, we have many more of those which, unfortunately, due to confidentiality, we're not allowed to talk about. So, a sustainable journey, diverse projects through the product life cycle. WAE designed and manufactured all the batteries for Formula E from seasons 1 to 4. The packs were designed, built and delivered in just 15 months and achieved over 99.5% reliability. Since then, we have been re-awarded the contract for the batteries for the third generation of the championship. And there is a key focus on sustainability as well as improved energy density, life cycle capability, fast charging and power. Extreme E. We were again announced as the sole battery supplier for the 2020 Extreme E program. Interestingly, this specific motorsport championship will highlight the impact of climate change and human activity on some of the world's most remote locations, while promoting sustainability and adoption of electric vehicles to help protect the planet. From our internal motorsport projects, we've developed many battery systems for road car applications. Some of these are vehicles that have been sold in the multiple thousands, and we are now moving into larger scale battery manufacturing with Hyperbat, our joint venture with Unipart Manufacturing. We are also diversifying the battery systems into other markets. A couple of these being the Anglo-American mining product and also sort of ocean-faring yachts. The battery pack in the mining product is well over 1,000 kilowatt hours in size for this fuel cell application. Finally, reuse. Significant experience in repurposing automotive batteries. The example I'm showing here was a project that we did on the EU Horizon 2020 program, where we took Second Life Nissan Leaf batteries into a stationary energy storage application. Clearly, the charge and recharge requirements of an automotive battery far outweigh those for residential purposes, and therefore, once end of life in automotive battery usage happens, it can be utilised for future residential use. So, sustainability. What does that really mean? We see that being used in many different factors, but it is fundamentally defined by the process of people maintaining change in a balanced environment in which the exploitation of resources, the direction of investments, the orientation of technology development and the institutional change of all in harmony and enhance both current and future potential to meet human needs and aspirations. UN Sustainability Goals are a call for all countries to promote sustainability. They recognise that ending poverty needs to go hand in hand with building the economic growth and the requirements from a social needs perspective. What does that mean to the automotive industry at a macro level? There are many levels to that. But interestingly, only on Monday of this week, Secretary General of the United Nations stated, to achieve net zero emissions by 2050, we need an urgent transition from fossil fuels to renewable energy. So what's historically been happening? Well, I think historically the industry has generally been concentrating on tailpipe vehicle CO2 emissions. The chart shown is from the US EPA, and Europe is clearly a little bit better, but what I was really wanting to illustrate here is that the industry has made some excellent advances in this time. However, to truly impact sustainability, a far more holistic approach is required. The whole value chain needs to be analysed to enable that sustainable growth across R&D, manufacturing operations, market, sales, and after sales. So, at a high level, we can understand that there are many factors that contribute to sustainability within the automotive sector. It actually creates a circular economy that increases the overall value chain and growth. We should be mindful of any form of environmental impact on the resources that we utilise and minimise waste at any opportunity, whatever our function is within the automotive industry. Interestingly, I am fortunate enough to speak to a number of different OEMs, and I've seen a significant change in this mindset over the last 3 or 4 years. Some have been doing it for longer, but certainly in the last 3 or 4 years, there has been an acceleration in this approach. Taking that top-down approach, there are already international standards for sustainable life cycle assessments. The question is, how does the automotive industry contribute across the design, materials, manufacturing, and use and end of life cycles? I've included a number of important midpoint factors to consider. This is just a mere snapshot. There are a huge amount more. The endpoints are clearly the outputs of any of our actions. The environmental, social, and economic benefits will be significant. One of the key things to note here, and I'll touch on this a little later, is the cross-pollination of our actions as engineers. If we design for one dimension only, it will always almost have a negative impact on another. So what is the industry doing? Well, if we look at the Advanced Propulsion Centre's technology roadmap for lightweight vehicle and powertrain structures, you can see a more holistic qualitative consideration being applied. Whether we are looking at design-led, materials-led, or manufacturing process-led, the considerations for sustainable life cycle analysis across those areas is being considered, rather than the historical cost, performance, and durability. One thing to note, I'm not going to go into the detail of each one of these areas, but if you're not already utilising the excellent roadmaps from the Advanced Propulsion Centre or the Automotive Council, I recommend that you do go there because they are an excellent resource. So, some considerations for this holistic design for sustainability. As I mentioned, it is not just looking at those traditional cost, performance, reliability elements that engineers would historically design for. There needs to be a consideration across all of the main factors, not only from an environmental perspective, recyclability, social, functionality, manufacturing, and resources. As I mentioned, they are all intertwined and very important in terms of getting that right balance. As I mentioned before, most OEMs are starting to take this into account, and I'll touch on that a little bit later on. So if we think about materials and materials alone, clearly the selection of materials and their resourcing is key to that sustainable development of automotive products. Still, at this moment in time, if we think about the equivalent CO2 per kilo, steel is still far and away the best solution. However, those things are changing, and as composites, mixed material technology advances, there is an expectation that this will change, and the trade-offs are required not only from a material production perspective, but also the use case. So clearly, CFRP, aluminium, magnesium have other benefits in use case. So powertrain has a historical direct link to sustainability, but we have come a long way since I remember a well-known UK car manufacturer having one engineered dedicated to fuel consumption benefits in 2001. Still only have 7.4% alternative fuel, including EV and base technologies, registrations in 2019. 1.6 BEV or fuel cell, but that is expected to rise. Whenever this is discussed from a powertrain perspective, well to tank, tank to wheel is always being considered. And this is clearly a contentious topic when we think about greenhouse gas. So if we look at some data that WA have collated over time, there is clearly variations in the makeup of life cycle greenhouse gases emissions between IC and EV vehicles. I've deliberately not put a scale on here. It is comparative data only. And if you go and look at various different resources, you will almost certainly get a different answer. One of the key points to note, and I think this is important when you consider when the government is keen to push electric vehicles, when you are starting to utilise renewable energy sources for electric vehicles and energy generation, the electric makes more and more sense. The current EU mix for energy creation is suggesting that we are still better over a life cycle greenhouse gas than the comparable diesel and gasoline products. One thing which isn't considered, and again, if we're thinking about that sustainability element, is air quality in urban areas and the knock-on benefits to human health. It shifts the dynamic further. Clearly, I don't want to say that electric vehicles are the only answer, and there, without question, needs to be a continuing development in hybridization, fuel cell, and alternative fuels. One size certainly does not fit all. Recyclability and component use. We've clearly had significant progress in this area, and there is an estimation that we will get to over 90% by weight recyclability or reuse within the next few years within the EU. Now, clearly the EU is generally ahead of the curve when it comes to these sorts of things compared to the rest of the world, but clearly there is further enhancement that's required to ensure that all of these new technologies that we're introducing and the recycling of materials, it continues. One point to add is that data for EV vehicles is relatively scarce when it comes to recyclability and reuse due to the limited number in circulation. So what have the OEMs been doing? Well, there's a question mark here against the world's most sustainable automotive company being BMW. It's not necessarily my statement, but some commentators have suggested that to be the case. If we look on the left-hand side, you can see that this assessment was done in 2013, and their full production use phase and the recycling of the BMW i3 had already been considered at that stage. Considering that the planning for that vehicle had probably gone on since 2008, the foresight that they have had over and above a lot of other OEMs clearly indicates that it's been at the forefront of their sustainability criteria moving forward. Even then, as we can see, the messages of renewable energy being utilised for the electricity generation makes a massive difference to the life cycle assessment of the i3. They clearly have a good rollout plan as well for continuing hybridization and electric vehicles. Toyota have a similar approach to considering life cycle assessment. Having had the joys of working for a Toyota Group company for 15 years, this is a very Japanese slide picture where they are clearly considering all of the various factors that I've already talked about and how they contribute to the vehicle life cycle. The organisation I used to work for over 10 years ago had a house on site that was specifically set up to allow sustainability to be considered across not only the use from an automotive perspective, but the reuse of energy and battery systems. Nissan as well are considering the life cycle assessments throughout the majority of their product range, as well as other technology developments. Clearly, maybe slightly behind an organisation like BMW, but it's clear that all of these organisations are considering life cycle assessment as part of their sustainability portfolio. And it's a given now from a marketing perspective that this is required for a large OEM. So, what is the WA sustainability approach? Three key areas connected to our core competencies: energy efficient performance, aerodynamic thermo simulation capability, fundamentally improving the performance and efficiency of any given product. The energy systems and technologies, so capturing, controlling, storing and deploying energy, and where possible, designing for reuse. Lightweight structures, high performance, composite and metallic technologies that not only give the right performance during use, but can be recycled or reused downstream. Aerodynamics and thermal management. If we're thinking about EV vehicles, the historical benefits of aerodynamics are clearly well known, and the benefits of fuel consumption or energy consumption have been around for decades. What is more and more important is the improved thermal management for electric vehicles. The increase of a vehicle's range by minimizing losses, but also the optimization and the vehicle range trade-off from passenger comfort and vehicle range across the ambient conditions. And efficient fast charging as well. So challenging the technology limitations across cell, pack and end of life as well. Ultimately, we take an approach to characterize and model as well as possible at a cellular level to ensure that we are maximizing the benefit at a cell-by-cell capability and a consistency across that cell. Maximizing the cell-to-pack ratio, providing the highest pack energy as much as possible from a packaging space, but also from a lightweighting point of view. And more importantly, especially as we move to more of a mobility as a service type of social requirements, control algorithms that will improve the health of the battery system and take a condition-based maintenance approach to keep the life of the pack and the battery systems as long as possible. Considering multi-cell chemistry approaches, ensuring that product can be as scalable and as adaptable as possible. An important element that has been considered over the last couple of years is consideration for second life uses at the conception of the design of the original use, and making sure that the algorithms are in place to make sure that we can understand and maximize the benefits downstream. On top of that, as a given, recyclability and sustainable disposal of any sort of material or componentry. Lightweighting. Our philosophy is that there is a paradigm shift that will come over time when we consider mixed materials as much as possible. Utilizing mixed materials gives the best benefit of mass and recyclability. There is the ability of having integrated systems for lightweight structures with our systems engineering and integration approach that should allow better packaging and a reduction in mass. Additionally, we have some novel composite manufacturing processes that allow the ability to utilize recyclable materials, as well as reducing the process time for the manufacturing of those composites. In summary, the journey the automotive industry has taken over the past few years has been positive. The industry is taking a more holistic life cycle analysis approach to sustainability, and despite the current disruptions in our lives, it is a very exciting time to be involved in this shift in the industry. Thank you very much for your time. I look forward to your questions.
Thank you very much, Dyrr. That gave me a lot to think of, and a lot of. It was really interesting to hear what's going on within the industry, what's going on within manufacturers and designers. I don't know if anyone has any questions. Whether anyone put any questions down in the chat. Sarah, was there anyone?
There's nothing as yet, but if you do have questions, please do enter them and we will ask them on your behalf.
As people are thinking, one of the things that I was wondering about, I had a few things that I was kind of sparked a little bit of, oh, that's an interesting thing. That would be a conversation to have. But one of the questions that I had there was whether the concept of taking a battery and having a second use for it after it's been used within a vehicle life, I thought that was an interesting idea. So it wasn't just stripping it down to its original materials and recycling it in that kind of traditional way that I would consider recycling, but reutilising as much of it as possible. Apart from like the home use kind of example you gave, what other ways are there? Are there other ways of which people are talking about using batteries in the future?
So I think stationary storage, whether or not it's residential or in an alternative location, is the key prime path. Just generally because of the charge and discharge sort of rates that are needed. They make things an awful lot easier for those batteries that clearly had a hard life through their automotive sort of usage. There is a thought around the potential to go down into sort of micro-mobility, less onerous sort of charging and discharging requirements. Generally speaking, a lot of the core transportation are very similar to where the charge and discharge is quite similar. And therefore, the cells will probably got to the end of useful life in that instance. So outside of pure residential, it's still very much just the stationary storage.
Okay, could I invite Aidan Turnbull to ask his question, please?
Hi dear, thanks for your presentation. It was really interesting to see how Williams is getting involved in this and what the general landscape's looking like. I mean, at the moment I work in the aerospace industry, and we've noticed, the general trend seems to be that there's not going to be one size fits all, not one size technology fits all. Do you think the automotive industry is heading down a route of no return with EVs, or with the alternative technologies like hydrogen, flywheel storage, etc., for sort of heavier duty vehicles? Do you think that will still have a place, or do you think we're almost set in an almost direct path now?
I think there are alternatives. I think flywheel storage, generally speaking, has probably had its day to a certain extent. I'll be glad to be corrected on that, but that was generally utilised because battery technology was not where it needed to be. Williams had a business for sort of flywheel storage. We sold that about 7 years ago, because battery technology had actually moved forward. I think, as I mentioned during this slide, one size doesn't necessarily fit all. But I think the key point is we are advancing on battery technology, and whether or not you are talking about hydrogen fuel cell, that still requires sort of battery technology to support that, or any fuel cell technology. The key thing for us, and the mindset that I'm in, and I'm sure the government and governments across the world are thinking like that, renewables for energy is, the driver. And once you can get that to be a significant percentage of the generation, and we don't have to rely on things like coal and natural gas, etc., that will allow us to utilise electric vehicles more and more. But alternative fuels need to be considered. Biofuels need to be considered. I used to work on diesel products 15 years ago, 18 years ago. Everybody was clamouring over biofuel, and essentially what happened there was that it slowed down, not necessarily because there wasn't the opportunity to exploit the technology, but they realised that all the farmers then wanted to sell crop for biofuel, and we wouldn't have anything to eat. So that's where I think there is a much larger holistic sort of consideration to look into.
That's a good answer, thanks. I think maybe looking at it from a whole lifestyle point of view, the materials usage is going to be massive for electric vehicles. There's obviously something's being considered by manufacturers. It's obviously something that's being considered by governments, but there's going to be new technologies. How far away do you think that we are from alternative battery technologies, moving away from lithium ion?
Yeah, so semi-solid state, solid state. I think you will see more and more concepts coming up in the next 2 to 3 years. From a pure production perspective, I would have thought the late 20s before we start getting into a solid state sort of position, and that will make that again. That will have a shift. There's various OEMs have different claims connected to that, but I would certainly say it wouldn't be before 2025.
Cool. Thanks for your answer.
Thanks, Steve. We've actually had quite a few questions come in now. I don't think we'll have time to answer all of them here and now, but I will put just a couple more questions to you. There's one question here. I've seen in Tesla's new pack design, the cells appear to be bonded in place, possibly to improve thermal conductivity. How do you see this approach impacting the ability to reuse the cells at the end of life? And do you think a trade-off will eventually need to be made between in-life performance and afterlife reusability?
So, really good question. There are absolutely there's thermal benefits to that. There's also structural benefits to the way that Tesla are sort of approaching that. But yes, that trade-off does need to be considered. I don't know the detail of what Tesla are thinking about from a sort of reuse recyclability perspective. It may have been published, but no doubt they will have thought of that. And I'm in agreement that is the type of thing that will need to be considered. As I mentioned, that in use versus the whole life cycle is shifting. People are thinking about it. And as I mentioned, in terms of our sort of design considerations, it without question needs to have that consideration. And people are doing it, and have been. My comment about BMW, looking into it and seeing how much foresight they had around that whole sustainability sort of process and life cycle is truly amazing. And I would suggest that people go and have a look at how much work they put in a decade ago to get that all right. But a great question.
And just one final question before we move to our second presentation. Regarding the CO2 per kilogram for the different materials, CFFP, steel, etc., how do you think this chart would change when the required mass of each material required for a given component is taken into consideration? steel components usually weigh considerably more than components made from the lighter weight materials?
That's a good question, and I've seen who sent that question. Mr. Alger, good to hear from you. Without question, and that's the trade-off that needs to be considered. I mentioned around that message. I sort of mentioned around the message that there is that trade-off. Clearly, from a materials production perspective, there is an impact. But when you then consider the benefits of mass of some of the other materials I mentioned, there's clearly performance benefits, and it's getting that right in terms of the sustainability versus cost versus performance that we were considering. One of the things that we are looking at significantly at WAE is the opportunity for more mixed materials, non-steel, but aluminium, composite materials, which not only utilize reusing materials, but we're trying to reduce the time to manufacture from a composite perspective. That's one of the key things that has historically restricted composite use as well.
Great, thank you very much. Thank you for all your questions, everybody. And as Sarah said, we will try and collate those and pass them on to Dyrr at the end, and allow Dyrr the opportunity to reply and respond to those questions for everyone to benefit from. But as time is not infinite and we have a limited amount of time today, we will move on to our next presenter, who is Jonathan Sewell, who comes to us from Millbrook Proving Ground. He has been working within the industry, working within motorsport, motorcycle engineering and the like. Jonathan has had a career within the academic area, so working in universities, primarily Coventry University, as a researcher and a lecturer. Jonathan's also worked with the Centre for Advanced Low Carbon Propulsion, working on thermal management of battery cells, modules and packs. So similar to some of what Dyrr was talking about with thermal management coming much more important as things are changing within the world of batteries. As I say, Jonathan is currently the technical trainer at Millbrook, making sure that the things that are done at Millbrook are in the safest way possible and being conducted to the best of the industry standards. And he's going to give us a presentation on battery safety. Take it away, Jonathan.
Thank you very much, John. Thank you for the lovely introduction, and thank you very much to Dyrr for a very interesting and insightful presentation as well. Hello, everybody. Today I'm going to be presenting a presentation about battery safety in electric vehicles. It's a bit of a hot topic, and there are quite a few concerns generally from the general public about electric vehicles, but we'll go through those as we go along. Firstly, we really need to understand why we're actually in this situation, or why we're seeing a shift towards electric vehicles. Well, it's all to do with, and this might be regurgitating what Dyrr presented, but we are being pushed to reduce our emissions. This is what the whole idea about reducing greenhouse gases and so on. And the government, the UK government, in fact, have decided that by 2050 they want to significantly reduce, if not end, the production of any greenhouse gases. And they've identified 5 key areas. Those are power, how we generate power, buildings, both old and new buildings, looking at aspects such as low carbon heating solutions. Industry is another area that they've identified. For example, looking at low carbon hydrogen production. Natural resources, so this looks at aspects such as food production and land management. And then we've got transport, and that's really what I'm going to look at the safety considerations of. But what is the transport, or what is the government's plan for the transport industry? Well, they've got this Road to Zero plan, which states very early on that they're planning for the end of conventional petrol and diesel cars and vans by around 2040. You may have heard in the news that there is some push to bring that forward some 5 to 10 years. The government's also planning to actually remove all conventional vehicles at around 2050 as well. So this is quite a huge push, considering that we know that the majority of vehicles on the road at this point in time are our conventional vehicles, our petrol and diesel vehicles. Are electric vehicles new? Well, the short answer is no. No, they're not. As between 1890 to 1910, there were a number of hybrid vehicles and pure electric cars. By 1915, most vehicles being produced were now gasoline or petrol-based vehicles. So there was a shift then. Is it just the UK driving for low or zero emission vehicles? Well, it won't come as a surprise that this isn't the case. Interestingly, China and South Korea are taking a different approach by pushing hydrogen as the future fuel. China want to have 1 million fuel cell vehicles by 2030 on the road. And as of 2019, they only had just shy of 2,000 vehicles on the road. South Korea have plans for by 2025 to have 200,000 hydrogen vehicles on the roads. So there's going to be a huge push. This presentation, as my get out of jail free card, isn't going to go into the pros and cons of hydrogen versus battery electric vehicles. We know that lithium batteries are very common, or lithium-based batteries are very common in electric vehicles. They're very common in electrical items as well. Really they came around in around 1980. Whereas if we look at lead acid batteries, which are more commonly associated with low voltage battery sources, electrical sources for conventional vehicles, they were around in 1859, around that sort of time. Lithium batteries, however, are classed as dangerous goods. And within the transport of dangerous goods, they have their own section. They have section 38.3. So you'll hear people talking about 38.3 and sort of section 38.3. And in that section, it states that all cells or batteries, lithium-based, shall be tested. And then it lists the test criteria for each of those cells and batteries. A cell, an individual unit, an individual battery, such as an 18650, quite similar to a AA battery. A battery is basically a grouping of cells, just to aid with a little bit of information there. And the cells and the batteries, as part of 38.3, they need to pass tests to be transported by road, sea or air. And this is before they're in items, before they're actually in products. So what about electric vehicles? Is it okay just for these batteries to be tested in 38.3 and for them to be not fine for OEMs to use in their vehicles? Well, not really. We know that electric vehicles are becoming more and more popular. We know that through this road to zero, there is a real drive to become the norm. So electric vehicles to be the normal cars that people will be driving. But even under normal driving conditions, batteries can be put under a series of demanding physical events, such as vibration from the road surface itself, going over speed bumps, might be a curb strike. It goes through extremes of temperature. And this is where UN ECE Regulation 100, or more commonly known as Reg 100, comes in. This is being designed or put together to test the electrical safety of the vehicles and also the rechargeable energy storage systems as well. As part of Reg 100, there are two parts to it. The first part, like I say, is about the electrical safety, and that covers these 4 items and others. So the protection against direct contact, the protection against indirect contact, isolation resistance, and functional safety. Functional safety basically meaning the fact that if you leave your vehicle in drive, you open the door, the vehicle has to give you either an audible or a optical warning the fact that the vehicle's still in drive. So what am I looking at this one? Well, protection against direct contact. Why do we need this? Well, OEMs don't want their customers to be going around and getting themselves electrocuted. It wouldn't be a particularly good news story for them. Part of the criteria is for them to check all electrical connectors for compliance, and it's all the high voltage electrical connectors. The high voltage side of the vehicle can be above 30 volts AC, RMS, and 60 volts DC. So we're seeing battery packs creeping up towards 4 figures nowadays in some vehicles. So getting up to about 1,000 volts DC. So we don't want the consumers, we don't want people, the general public, even engineers, to actually be able to get in contact with a live high voltage energy storage device. How do they check it? Well, they use this probe, the probe that's shown on the right hand side, known as the British Standard Finger Test. They use this probe in different orientations into the connector, into an open connector, to try and actually make contact with the high voltage conductor. It passes if it doesn't make contact. If it passes using the finger test, such as this, the connectors are given their IP rating, IP 2 numbers, and then assigned with a B at the end. These type of connectors can be fitted anywhere in the vehicle except for in the passenger compartment and the luggage compartment of the vehicle. For those cases, they use a different test where it's not quite, it's a thinner probe that actually has to go in, because the general public are going to actually be in those vehicles, or the consumers are going to be in those vehicles. Another example is the isolation resistance, or an isolation resistance test. The HV electrical circuit doesn't ground to the vehicle chassis. It's isolated from the chassis. This prevents the chassis from carrying the high voltage, or basically potentially fatal voltages, from the energy storage system, which means the fact that the user should not be able to get themselves in contact with this high voltage system on a vehicle. And it checks the isolation test, it checks the isolation resistance between the high voltage system and the vehicle chassis. If there is a presence detected, it basically doesn't mean the fact that it's a complete fail, but it's within certain realms. Fuel cell vehicles have a slightly different regulation to battery electric vehicles or hybrid vehicles, because of the fuel cell tends to produce, a hydrogen fuel cell tends to produce water anyway, so it gives a slightly different resistance across, but it gives you an idea. Part 2 of Reg 100 is looking at the energy storage system. So this is to do with mainly the battery packs, either as cells, modules, or packs themselves. Selling a bit of what Millbrook can do, we can do the majority of these tests. We do have limitations on vibration, as in the size of the packs of which we can do the vibration tests on, but the majority of the rest of them, we can actually physically do these tests, and we do these tests. And there's a lot of investment going in. So we've got a list of tests which include vibration, thermal shock and cycling, mechanical shock, fire resistance, external shorts protection, overcharge and over discharge protection, over temperature protection and emissions. This is all on these battery packs, modules and cells. If we look at the thermal shock and cycling, what does that test actually involve? Well, it's 6 hours at 60 degrees Celsius or higher. Then it has to drop down to minus 40 degrees for at least 6 hours. And that crossover, that ramping between those two temperatures, or the cooling down of the pack, needs to happen within 30 minutes. Then it's cycled. When I say it's cycled, it's heated back up again, it's cooled down, it's heated back up again, it's cooled down, and it goes through a cycle of 5 times. After it's been through this cycle, it's then left for 24 hours at around about 20 degrees Celsius, plus or minus, I think it's about 10 degrees Celsius. And the pass criteria is the fact that if there's no leakage, so no electrolyte leakage, there's no rupture, I'll explain what rupture is later, fire or explosion. We then have, again, I'm not going to go through every single one of these, I've just got a selection of 3. We've got mechanical shock. What is mechanical shock? Again, it's to do with, it's to simulate a harsh deceleration or acceleration, simulating a possible collision in the vehicle. So you've got high accelerations when you crash, or when the vehicle is actually physically crashed. The test can be conducted both as a full vehicle or, as the figure here shows, a battery pack on our servo sled. We can do it on our servo sled because we can do it as a reverse, basically doing it as an acceleration, as a deceleration value, and we actually get the pulse that they're actually using is quite is regulated for it to be classed as an approved or a valid test. We basically shoot the battery pack down our sled while having all the monitoring on, and then it's basically a pass and fail criteria of which it needs to pass, or hopefully needs to pass, or hopefully does pass. We then have some people see it as the more exciting side of things because it includes fire. It's quite a strange test, to be honest, especially when we're doing a drive for zero emissions. This test involves basically burning petrol. And the test is to replicate a crash between a conventional vehicle and a electric vehicle. And the petrol vehicle, the fuel actually is on the floor underneath the electric vehicle and it ignites. And what's going to happen to the battery pack? The test includes 4 phases. Igniting the fuel, allowing it to preheat if the fuel is less than 20 degrees Celsius. Then the flames are actually put, or the battery pack is actually placed above the naked flames. And the battery pack's left there for 70 seconds. After this 70 seconds, it can either continue for another 60 seconds, being exposed to the naked flame, or it can have a indirect exposure, basically a screen that slides across the flames. Once this 2-minute and 10-second test has been completed, you've got the removal of the flame from the battery pack, and then we monitor the surface until it's ambient, or at least the pack is actually reducing in temperatures over a 3-hour period. The pass criteria for this test is the fact that there's no evidence of explosion. So there's no mention of flames here or fire. There's no mention of leakage or rupture. The pass criteria is the fact that we don't have explosion. So I spoke about very briefly the fact that there's leakage, there's venting, there's fire, rupture and explosion. But there's got to be a classification of these outcomes from battery testing. And one example of which is used in Europe is the European Council for Automotive Research have produced basically with this table that you can see here. Hazard level 0 through to 7. 0 being no effect whatsoever, up to the extreme of explosion. Explosion is basically a disintegration of the cell. I'll put my teeth in for that. We've got the one lower down, or one step lower, so hazard level 6, which is no explosion, but we've got flying parts of active mass. We tend to see this as the casing of the cells actually still intact, where the internals have basically been ruptured or shot out of the cell. We've got flame as well, the next level down. So flame, when you can actually see fire or a flame coming from the cell itself. Venting, so this could be venting of gas, but the gas is not actually igniting. Leakage, we've got, tends to be talking more about the actual electrolyte itself, as in a leakage you tend to actually see a fluid coming out. Defect or damage, which is irreversible, so the cell actually needs repair or it's end of use for the cell. And then you've got passive protection activated. So some cells have got passive protection against some of the tests that they are put up against, such as overcharge protection and so on, where the actual protection device has failed, which it should do, but the actual cell itself is absolutely fine and can be reused. We look at guidance from the HSE on how we can go about working on electric vehicles and batteries safely. And they've identified 8 criteria, or 8 risks associated with working on electric vehicles. Most people tend to have a fear of electrocution when it comes to electric vehicles. However, that's only one of the 8 that HSE have identified. Other people have a bit of concern about electric vehicles and electric fires, or recovery of damaged electric vehicles or crashed electric vehicles. That's all covered really in this, and it's not really the risk of electrocution, because it being the main problem, because we don't really see in the everyday use of production vehicles anyone getting electrocuted. We do see in the news, be it national or world news, the fact that some electric vehicles have caught alight, and there have been issues with being able to extinguish or manage these fires. But eventually they do either burn themselves out, or they can be controlled by the application of usually water, which is quite scary when you think about mixing lithium with water. But at the end of the day, most of the vehicles that we're seeing on the public roads, getting to the actual battery packs themselves is quite difficult in the case of a fire. So basically you're trying to keep the pack as cool as possible or remove the heat from the pack. You're not really trying to extinguish the fire. So all in all, are electric vehicles dangerous? Well, there's arguments both ways, but generally speaking, they're no more dangerous than a conventional petrol or diesel vehicle. There should be no concerns from, or no heightened concerns from the general public about electric vehicles. Electric vehicles are going to become the norm, be it correctly or incorrectly, be it the best option or not the best option. That's not for me to see. And being the automotive industry, they react so quickly to changes in legislation or changes in ideas. If we look at one stat, which I managed to get, a UK stat for the call-outs for the London Fire Brigade, which attended just shy of 2,000 vehicle fires in 2019. 54 of those were electric vehicle fires, and around 1,900 were conventional vehicle fires. When we look at those stats themselves, they don't really give you much information on the cause of the fires, but it's assumed that a lot of these fires, vehicle fires that they actually attended, especially in London, were actually due to arson rather than the actual vehicles failing. And that's really what we want to get people to be seeing, is the fact that the vehicles are safe. The vehicles are going to become normal. And the general public don't really need to have much worry about them. It's got the same idea of basically being plugged in. Well, it's plugged in just like charging your phone. It just takes slightly longer. And that's pretty much where we are with the safety on electric vehicles. We've just gone past about 10, well, we're just about 10 past now, aren't we? So I'll invite any questions.
That's great, Jonathan. Thank you very much. Really interesting, really great to hear that the vehicles are safe in general, which is good because you hear a lot contrary to that, certainly in the general press. The scaremongering stories always sell more papers. But Sarah, have we got any questions come through for Jonathan yet?
Yes, we have. First question is, are there differences in world and EU regulations, and will the UK have its own guidelines or regulations?
That is a conversation of which I've started having within the business this week, really, about the UK and EU regulations. And I think the answer to that is watch this space. When it comes to Reg 100, it was meant to be a world harmonised regulation, but the US, I don't think, have joined or signed up to it, and neither did China, which ironically are the two biggest electric vehicle consumers, I suppose. So basically really watch this space, and yes, there are also different regulations for different countries or different parts of the world.
Okay, a further question. What work is being done to actively cool batteries whilst they're charging to enable fast charging? How feasible is it to charge electric cars as fast as refuelling?
It's quite poignant, but I read an article, must have been yesterday, maybe the day before, and it was on a new set of cells that have been developed that can actually take a full charge in 5 minutes. And they're saying the issues with those cells are actually the ability for the charger to deliver the power requirements, rather than actually being limited by the cells themselves, the battery pack. What work is there being done in the thermal management side of it? A huge amount. There's a lot of work on the actual chargers themselves. I know there's been an incident with Moto E where the actual chargers were at fault because they actually had batteries built into the fast chargers themselves, so they could actually deliver a faster rate to the motorcycles, and they failed, and actually the result was all the vehicles, all the motorcycles were actually burnt down one evening. I think it was 16 or 18 motorcycles. So it's not just the actual thermal management of the batteries, it's also, I suppose, the thermal management of the chargers as well. So yeah, people are looking at obviously water glycol mixtures, active and passive cooling techniques, looking at tab cooling. So instead of surface cooling of the cells, and actually looking at trying to cool the tabs, because that's where they're actually getting, or where people see quite high temperatures of the cells. If you're only cooling the outsides, the surface of the cells, you've actually got obviously the heat. It's being generated. You've got a heat gradient, and the cell gets warmer the closer to the centre you get. The university that I came from, part of their research was looking at the temperature gradients in the centre of the cells. They're actually producing prototype cells with where they had the ability to actually measure the temperature in the centre of the cell at any point using fibre optics, in fact. So yeah, there's an enormous amount still to be done, really, on the thermal management side.
Thank you. And just one final quick question. Are there safety guides to fighting a battery fire?
There's information out there. We at Millbrook have a on-site emergency response team, and we've been conducting our own training on how to deal with incidents involving electric vehicles, because Millbrook's we do the testing of the vehicles, the components, and we've also got the tracks as well. So we can have incidents either in buildings, around buildings, on tracks, which can involve electric vehicles. And the more testing we're going to be doing, arguably the more incidents we're going to have. It's just the nature of the beast. The NFPA, so the National Fire Protection Agency, has a lot of information, and they've done a lot of research into it. So dealing with an electric vehicle fire, is it okay to use water? Is there any at the brass end of their hose, if they're actually hosing the vehicle? Is it actually conducting any electricity up the water flow and onto the brass end? And they state the fact that no, because they've done the test work of it. But guidance-wise, it's quite thin, I believe, on the ground at the moment. But I would stand to be corrected on that.
Wonderful. Well, thank you. Thank you very much, Jonathan. I think that's probably all we have time for. Thank you, everyone, for staying on to the end. Sorry if we've overrun for some people and they now have to run off. Just to remind you that the EIS is going to have further webinars coming up. We have another webinar in February, again aimed at younger engineers, but primarily to focus on the noise and vibration and shock domain. What is it and why should I be interested in it? So if you're interested in that, or it sounds interesting to you, or you know someone who would be interested, please do let Sarah know via email. You can also get in touch with us or stay in contact with us on our LinkedIn pages. And yeah, if you would like to know more about the EIS or the Young Engineers Forum or anything else, please do get in touch with Sarah, and she'll be more than happy to add you to our mailing lists and to get in touch with you.